Okay, let's continue where we stopped last time. I just began in the last few minutes of the last lecture to talk a little bit about Kotler spacetime, Schwarzschild spacetime with a cosmological constant. The metric, I just wrote the metric down without deriving it. You can derive it in complete analogy to how you derive the Schwarzschild metric. And what you get is, in addition to the Schwarzschild term, a term which involves the cosmological constant, lambda, and the same function in the denominator of dr squared, and the usual angular part. Let me write just the omega squared for this. Okay, so you see what the lambda does is relevant if the R is big. Yeah? So this term plays not a big role if R is very small. So if you have a Schwarzschild black hole, and now you crank up the lambda, you switch on a lambda which takes some small but non-zero value, then in the neighborhood of R equals 0, in the interior of the black hole or near the horizon, the situation will be not much different from Schwarzschild. But farther away, then this term becomes more dominating. And actually, what this term does in particular is that the spacetime is no longer asymptotically flat. Yeah? So if you have this term here also, and you send R to infinity, then this approaches 1, and the whole metric approaches the Minkowski metric. Yeah? If you send R to infinity. But with this term, Minkowski is not approached. Yeah? Rather, this term gives a strong deviation from Minkowski spacetime. So we are no longer in a asymptotically flat situation. And this has a consequence that it's not quite so obvious how to interpret the integration constant Rs. It comes about in the same way as the Schwarzschild integration constant, but in the Schwarzschild case, we could use the fact that far away from the center we have Newtonian-like situation, and we could compare with the Newtonian gravitational theory. And this told us that Rs must be 2gm over c squared. This doesn't work, at least not with a big lambda. If lambda is very small, then you still have a region where this is small in comparison to this, but this is even smaller than this here, so that this is still a good approximation, and then you can use Newtonian theory in this range. So as long as lambda is small, we can still identify Rs with 2gm over c squared. If lambda is big, then this is no longer true. Okay, and what we have done already is that we have looked at this function here in the denominator and investigated where the zeros of this function are. The zeros give us a horizon. Yeah, for Schwarzschild, the horizon is at R equal Rs. But with this term, the situation is more complicated. You see, if you set this equal to 0, then you get a third order equation. Yeah, you multiply the whole thing with R, then you get a cubic equation. And so you will, in general, expect more than just one real root. And actually, we did this already. We found that for lambda smaller than 0, we found that there is one horizon. And well, if lambda is equal to 0, then we know, of course, that there is one horizon. There's a Schwarzschild. And the horizon is at Rs. Now, if lambda is negative, then you have a positive term here. This means the 0 moves to the left. So you have here a 0 which is between 0 and Rs. So the index h stands for horizon. Yeah, that's the radius coordinate of the horizon. So here the horizon is between 0 and Rs. And then comes the interesting case. We have seen that for lambda bigger than 0, there are two cases to be distinguished. If lambda is smaller than a certain lambda c, c stands for critical, which was 49 divided by Rs squared, then we have two horizons. And they are situated between Rs. So here's the first horizon, RH1. Then there comes the second horizon, and they are between Rs and infinity. And then the limiting case, the critical case, lambda equal to lambda c. There the two horizons come together. You see, if I approach lambda equals 0, then this horizon goes to Rs and this horizon goes to infinity. If I go in the other direction, if I go towards lambda c, and the two horizons come together and they meet somewhere, and actually we calculated last time already where the 0 is, we have, that's what one calls a degenerate horizon. Yeah, it's a double zero of this degenerate horizon. And it is at, so we have two zeros, RH1 and RH2, but they coincide. And what we found was that this is at 3½ Rs. And then if we are bigger than this critical value, lambda smaller than infinity, then we have no horizon. Yeah? This quantity has no zero in the domain between 0 and infinity, so there's no horizon. And that's what we have now to interpret. And well, if there are horizons, and if we want to know what's going on near the horizons, then we do the Eddington-Finkelstein stuff. Yeah? What we did with the Schwarzschild spacetime in order to understand what's going on at I equal Rs was that we introduced Eddington-Finkelstein coordinates. And the same thing we do here. So we consider radial light rays. Yeah, the radial light rays are automatically geodesics. So we don't have to care about the geodesic equation. This follows from the symmetry, that if a light ray goes along a radial line, then it must be a geodesic, just for symmetry reason. And so we have just to equate this expression to 0 with the angular part equal to 0, because we have a radial light ray. So we have minus c squared 1 minus Rs over r lambda over 3r squared dt squared plus dr squared divided by the same quantity. And that's it. Oops. Yeah, no angular part because we have radial geodesics. Okay, let's rearrange this a little bit. Then we have plus minus c dt is dr divided by 1 minus Rs over r minus lambda third r squared, right? So we have two signs, of course, one for outgoing and one for ingoing radial light rays. And well, in the case without lambda, we could easily integrate this. This gave us, if we integrate this over, this gave us the tortoise coordinate. Yeah? And the two things together, t plus or minus the tortoise coordinate, was the ingoing or outgoing Eddington-Finkelstein time. So we do something similar here. We call this dr star. R is a generalized tortoise coordinate. But now it's not so easy to write R star in explicit form. Actually, it can be written explicitly. This is, well, if I multiply with R, I have a cubic in the denominator. And the roots of a cubic can be determined. Yeah? There are several versions of closed form formulas for the zeros of a cubic. But all of them are fairly ugly, and I don't want to go into this here. So I don't write this down. But in principle, you could decompose this cubic, which arises here if you multiply with r. You could determine the zeros of this cubic, and then you could write the function r star in terms of this cubic. So what we need to know is just that the dr star is defined by this expression. And now we have for ingoing generalized Eddington-Finkelstein coordinates. Coordinates, they are our old r coordinate, we don't change this, and the time t tilde, which is, wait a minute, the ingoing there was a minus sign, right? If t is increasing, r should be decreasing for the ingoing one, so I have to choose a minus sign. And if I take this to the other side, then I have t tilde is Yeah, what now? It is t plus r star. Is that true? C, of course. C t tilde is this. Okay. And now let's plot this. Let's begin with the old coordinates. So we have to distinguish the three cases, of course. Let's begin with lambda smaller than 0. And then we have here our diagram, say R. I begin with the ordinary Schwarzschild coordinate. If we have lambda smaller than 0, we have one horizon. It's not at RS, it is at some different value, but apart from this, the situation is more or less the same as it was in Schwarzschild. So we can read that this expression here, it has zeros at the horizon, and actually with a minus sign, it is positive for small radii. Right? It's exactly the same thing as for Schwarzschild. For Schwarzschild, this expression was positive inside the horizon and negative outside. So outside t was a time coordinate, inside it was a spatial coordinate, and the same thing is here. Yeah, if lambda is negative, then it's exactly the same thing here. So we have the same relations as for Schwarzschild. The light rays are a little bit deformed, but qualitatively they are the same thing. Here's the light cone, and they are going out here like that, and here the light cones are like that. So outside of the horizon we have a nice static space-time. Yeah, so observers can hover at constant r coordinates, but inside the horizon this is impossible. Inside the horizon everything has to go to the singularity, and it still is a singularity at r equals 0. Yeah, because we still have the 0 here. The lambda doesn't change anything near r equals 0. Yeah, near r equals 0 this is irrelevant. So we have the same kind of singularity here on the axis as we have for Schwarzschild. And now we switch to our Eddington-Finkelstein coordinates, to the ingoing ones. So I plot t tilde over r. I have the horizon at RH, and now the things fit nicely together. So we have transformed the ingoing ones onto straight lines. Oops. And yeah, the outgoing ones, they are even stronger deformed. Yeah, so they are now something like that. And the outgoing ones are coming here. Okay, so we have, let me draw a few light cones. We have, let me write this here. So we have here a light cone at the horizon. The light cone is tangent to the horizon, and here it's like this. So if you are outside of the horizon, you are free to move inward or outward, but if you are inside the horizon, you have to go towards the center. So for lambda smaller than 0, situation is pretty much the same as for Schwarzschild. Everything is a little bit deformed, but qualitatively there's not much difference. Situation is quite different if we are in this case here, where we have two horizons. So now let's do this case. So we have to see where is, so again I begin with a Schwarzschild coordinate. So we have to check where is this function in front of the dt squared, where is it positive and where is it negative. So the situation is not changed near r equals 0 by a lambda. So we still have t being a space-like coordinate inside. Yeah, t is space-like inside and time-like outside. So we have the light cone still in this way. Okay, I need a second horizon. I need a little bit more space. Here's the second horizon. So they should be parallel, these lines. So the light rays come down asymptotically from the horizon, as I did in the case lambda smaller than 0 or lambda equal to 0. But then the thing has also to diverge at the other horizon. And how can this be done? Obviously, it must behave like that. Yeah? And if you study this integral here, you can actually derive this behavior. So it's not just guesswork, you can really check this. And the light cone is like that. So we have between the horizon, we have a static region. Here an observer can stay at a constant r-coordinate. Inside he has to move inward, and yeah, outward we have, if we do a, oops, we have something like that. They go out to infinity. So like that. Oops. And the light cones are like that. So outside of the outer horizon, t is again a space-like coordinate. Yeah? This means in this area, outside of the outer horizon, you cannot stay at a fixed r-coordinate. So the situation is quite different from the region around the star, what we are used to. Yeah? Something new happens here, and because this happens at a far distance from the center, and as it is caused by lambda, which is called the cosmological constant, one calls this a cosmological horizon. Yeah, this is a black hole horizon. The situation is very similar to what we have learned about black holes in the Schwarzschild case, but this is a horizon of a different kind. It is made by lambda, so it's called the cosmological horizon. And in between the two, there is a static region where the observers can move around if they want to watch the black hole. And the second horizon is very, very far away from the center as lambda is small. Yeah? So we believe that in our universe we do have a lambda which is different from 0. We believe that it is positive, but we also believe that it is tiny. Yeah, it's something like 10 to the minus 50. Lambda is an inverse length squared. And the length, which corresponds to lambda, is 10 to the 55 meter, something like that. Yeah, so if you have this in the denominator squared, so it's really tiny. Okay, so this is this case, and again we can switch to Eddington-Finkelstein coordinates. Then, actually now you have two possibilities. You could, well, I have drawn the light cone here. Of course, you could also consider this as a future cone, and you could glue a different kind of horizon here, yeah, where the signals go in the outward direction. But if we introduce the ingoing Eddington-Finkelstein coordinates, so if we map the entire range of the ingoing, oh, they should be straight lines, the ingoing light rays onto straight lines, then we get something where we have a black hole, and also this horizon can only be crossed from the outside to the inside. So let me see, the outgoing light rays are like that. So we have here in the middle, we have something like that. Oops. And here we have something like, no, there's no bending. It's monotonous, like that. So here we have the light cone. Here we have the light cone. Here we have the light cone. So if you are in this region, you can move outward or inward as you like. In this region, you can move only inward, and in this region, you can move only inward, if you do this extension. So if you start here, and whatever you do, you may move around in any way you like. As long as you move at subluminal speed, you will have to cross this horizon at a finite time. Yeah? And then you are free to move around here. And if you are stupid enough to cross the second horizon, then you will end up in the singularity. Yeah? So that's... Question?
When we are in the first static region, so theoretically we can't move to the outside region, right?
This is a static region. From here we can move only inside, yeah, to the inside.
So we can't go.
Yeah. You see what the light cones are doing, yeah. So if you are in this region, then you can receive signals from this outside region, but you cannot send signals to the outside region. And yeah, this is now the Eddington-Finkelstein diagram, R and T tilde. So you see, for big R, the situation is really completely different than for Schwarzschild. So in particular, you cannot have observers, yeah, which are static at an R coordinate at arbitrarily big radii. Okay, and then the third case. So if this lambda has a physical meaning at all, then it's this case which is relevant, yeah, where we have a small positive cosmological constant. But I said already that even in this case, it's hard to believe that this has any physical relevance, because if we are so far away that the lambda plays a role, then we do not longer talk about an isolated mass in the universe. But the neighboring masses already play a role, which are ignored in this whole setting. Yeah, we talk about a spherically symmetric solution, where no other matter in the neighborhood is considered. And at this distance, where the lambda plays a role, of course, the neighboring stars would have to be considered. Yeah.
But what if you consider a case where we approximate a galaxy or galaxy cluster by this metric?
That's better than a star, definitely. Yes. Okay, you might. Yeah, well, actually, a spherically symmetric model for a galaxy or for a galaxy cluster is not too bad. I say, well, galaxies are not exactly spherical, right? If you look at these nice pictures in astronomy books, you see the spiral galaxies and things like that. But actually, if you approximate this by a mass concentrated in a central region and spherically symmetric distributed, you get a fairly good model. Yeah? Because the majority of the mass is actually concentrated almost spherically symmetric around the center. So it's not a very bad model for a galaxy. Of course, it has its limits, but it's not a totally idiotic model, let me put it this way. So, and in this sense, maybe if you have, or maybe you could even consider a galaxy cluster. And then, maybe it might be a reasonable approximation to take the lambda already into account, but the neighboring galaxy clusters, but to ignore the neighboring galaxy clusters. So, maybe it's not completely out of the question to use such a model. Okay, and then we have the case where lambda is bigger than lambda c. So then we have no horizon. You might say, oh, that's fine. Then we have a regular space-time. Everything is nice again. But no. It's even actually the most pathological case of all what we study here. In this case, there's no need for introducing the Eddington-Finkelstein coordinates, because our old coordinates already cover the whole exterior space-time, except at r equals 0. And what we have is, well, near the singularity, we always have the same behavior, because the lambda term plays no role near the singularity. So it begins, as it always begins, near the singularity, and then it goes out to infinity. So we have something like that. But the light cones are like that. So T is everywhere space-like. Yeah? So the space-time is not static. It's nowhere static. It's everywhere dynamic, in the sense that I cannot hover at a constant r coordinate, and I'm sucked towards the singularity, and I cannot do anything against this, because I have to stay inside the light cone. And this means that wherever I start, if I start at a finite distance, I will end up in a finite time in the singularity. So this is in the case lambda, in all other cases we have discussed before. There was a region where the space-time is static and where I am safe. As long as I stick to this region, nothing will happen to me. Here, there is no regular region, no region where I can evade the singularity. Yeah, I have to go to the singularity. Well, maybe you have heard that there's a notion of a naked singularity, which means a singularity without a horizon. Yeah? If you have a singularity, like here at r equals 0, but no horizon around it. But so that's what we have here, actually. We have a singularity and no horizon. But this is not what one calls a naked singularity. By a naked singularity, one means something where an observer is far away from the singularity, and he can receive signals from the singularity. So he can see the singularity. In this sense, it is naked. Here, there's no horizon, but nonetheless, the singularity is not visible to any observer wherever he is. Yeah? Because no signal can come from the singularity towards the observer. So this is, I don't know if there's a special word for this, but I would not call this a naked singularity. We will come back to naked singularities when we speak about the Kerr metric. In the Kerr metric, we have, if the spin of the black hole is big enough, then we have a naked singularity in the sense that I can see the singularity from a distance. If I'm outside, far away, at a safe distance, I can receive signals which come towards me from the singularity. That's what not happening here. Okay, so these are the three cases. And I said already, more or less the only interesting case from a physical point of view is this here. And we will now discuss a little bit geodesics in this space-time. So, well, actually a few things can already be deduced. So, for instance, I will talk about bound orbits in a minute. So we want to ask in which domain is it possible for a freely falling particle to go around on a bound orbit, oscillating between a maximum radius and a minimum radius. And it's already clear that in the case lambda smaller than 0, this is possible only outside of the horizon. Or let me show it with this picture. Only outside the horizon. Because if an orbit ever enters into the interior region, it can never come back. So it cannot be periodic. It cannot be oscillate between a minimum and a maximum. Yeah? So here, the bound orbits are certainly confined to this region, as in Schwarzschild. In Schwarzschild, we also had no bound orbits in the interior of the black hole. How is it here? In this case, let me show this picture. I'm not sure if anything can be read from this picture. I will produce nicer pictures for the lecture notes. So here we have the static region. You can have bound orbits in this region. As soon as a particle has crossed it cannot cross this horizon in this direction, it could cross it in this direction. But if it does so, then it can never come back. Yeah? So there can be no bound orbits which enter into this region. And there can also be no bound orbits which enter into this region, because again, they cannot come back if they have crossed the horizon. So bound orbits are confined to this region. Yeah, in the case that lambda is smaller than lambda critical. And in this case, what do you think about bound orbits in this case?
No bound.
I'm sorry?
No bound orbits.
No bound orbits possible, because R is monotonic along every time-like curve. Yeah, because the light counts open to the left. So the R coordinate must be decreasing along any time-like curve. And then it cannot be periodic. Cannot come back to a bigger radius. So only the static region only in the static region can bound orbits actually live. And we will also, in particular, ask about circular light-like orbits. I hope everybody remembers that in the Schwarzschild spacetime we have this circular light-like orbit at 3½ RS. And again, it's clear that if there are light-like circular orbits, we will check this in a minute, then they can exist only in the static region. Yeah, because also light rays cannot cross the horizon once in the one direction and then in the other. So they have to stay on one side of the. So if the R motion is supposed to be periodic, then it has to stay on one side of the horizon. So if there are circular light-like geodesics, they will exist in this region here, and here they will exist in this region. And actually we will see that they do exist. They cannot exist here. Okay, I think I need a little bit space.
So even though crosses this second horizon, does it mean that he's going to reach infinity in this coordinate?
I'm afraid I just erased what you were asking about. So if an observer crosses which horizon?
The second horizon,
the cosmological one.
Yeah.
So this must be, if it is a black hole space-time, it must be from the outside to the inside. Yeah, that's the direction in which you can cross the cosmological horizon. If you do this extension. Yeah, you can also make another extension at r equal rh2, this outer horizon, where the horizons cross in the other direction. But this cannot be done with the ingoing Eddington-Finkelstein coordinates. Yeah? So in the latter case, you would move always in the outgoing direction if you are moving on a time-like curve. So you would necessarily end up at infinity. Yeah? So you would have to move outward for all your life. Yeah. Yeah, of course, you could for all these extensions, you could also do the time reverse situation. Yeah, so then you would get a white hole here. Yeah, if you just do it with the outgoing Eddington-Finkelstein coordinate, and you could also do it for the case with two horizons. There you have the possibility you can do it one way at one horizon and the other way at the other horizon, if you like. And then you can ask the question, what is the maximal extension? Yeah, I briefly mentioned this for the Schwarzschild case. This was the Kruskal extension. This was actually maximal. And I told you that I believe that the Kruskal extension has no physical meaning because it contains regions which are just mathematical constructions, but according to everything we know, they will certainly not be realized in nature. And the same thing is here. So for this reason, I don't discuss this maximal analytical extension. It's mathematically quite funny, but I have serious doubts that it has anything to do with physics. Okay, so let's talk about the geodesic equation. I left the metric up there so we can read what the Lagrangian is. So we have and I will discuss the light-like and the time-like geodesics one after the other. So the Lagrangian is now what? It is minus c squared 1 minus rs over r minus lambda third r squared t dot squared. Dot means derivative with respect to an affine parameter, which in the case of a time-like curve is chosen to be proper time. In the light-like case, it's just any affine parameter. So r dot squared divided by 1 minus rs over r minus lambda third r squared. And for the angular part, I consider only the motion in the equatorial plane, as we can always do if we have spherical symmetry. Yeah, because the initial direction of a particle or of a light ray defines a plane. Yeah, together with the radial direction, it spans a plane, and the motion must stay in this plane because of the symmetry. Yeah, it cannot deviate either this way or that way without violating the symmetry. So for this reason, we can restrict to the equatorial plane, as one always does when one deals with spherically symmetric spacetimes. So that's the Lagrangian. And you see, as before, the metric coefficients are independent of t and of phi. So we still have these two nice constants of motion, E and L. So the t equation of the t component of the Euler-Lagrange equation is d by d. Let me write it this way: dl by dt dot. If I take the derivative of this must be 0. Yeah, because dl by dt is 0. dl by dt is 0. So this is 0, which implies that dl by dt dot is a constant of motion. dl by dt dot, and one calls this with a minus sign e. the energy. And what is it? The minus sign is convenient because it kills this minus sign. And then we are, oops, that's a dot, c squared 1 minus rs over r minus lambda third r squared t dot. Okay, that's our first constant of motion. And the same thing as with the phi coordinate. dl by d phi dot is also 0, because dl by d phi is 0. There's no phi anywhere. So that's what one calls L, the angular momentum, dl by d phi dot, and this is r squared phi dot. Okay, and now we have to distinguish the light-like case and the time-like case. So for light-like geodesics, let me begin with this case. We have that this must be 0. So we have 0 is minus c squared 1 minus rs over r minus lambda third r squared t dot squared. So r dot squared 1 minus rs over r minus lambda third r squared plus r squared phi dot squared. Okay, and because we know already the radial light-like geodesics, we have used them when talking about the Eddington-Finkelstein coordinates, we can use the parameter phi, the coordinate phi, for the parameter of our light rays. So I'm interested in an expression for dr by d phi, so it's a good idea to divide by phi dot squared. Yeah, then I get here in dr by d phi. So I multiply with 1 over phi dot squared, and I get what? Oops. I get 0 is minus c squared 1 minus rs over r minus lambda third r squared t dot squared divided by phi squared plus r dot squared divided by phi squared, that's a nice term, divided by the same thing, plus r squared. Okay, that's what I want to have, and these expressions can be expressed in terms of our constants of motion, E and L. Yeah? So T dot is E divided by this, and phi dot is L divided by R squared. So I insert this here, and I have minus C squared, 1 minus RS over R lambda third R squared. So T dot squared is E squared, divided by 1 minus RS over R minus lambda third r squared, whole thing squared, and c to the 4. And I have to divide by phi dot squared. This is L squared divided by r to the 4th. Okay, that's the first term. Here I use a chain rule, so this gives me r as parameterized by phi. And this is r squared. Okay, and I can solve for, here I can cancel the bracket. And I solve for dr by d phi squared. This is what? So I take this to the other side. I multiply with this denominator. Then I get e squared divided by c squared L squared r to the 4. And then I have r squared times this bracket. No, it's minus r squared, right? It's minus r squared. Okay, so we see that I get another term with r to the 4 here. So I combine the two, and I have minus is plus lambda z r4 minus r squared plus rs. That's it. Well, we have done the same calculation before without lambda. Of course, we got this expression here. Yeah? And now we have just this old constants of motion modified by the lambda term. That's the only way in which the lambda term enters. Yeah, it just gives a it modifies our constants of motion. Well, our light rays are labeled by certain constants of motion. And now they are labeled by different constants of motion. But, well, this is a constant, and this is also a constant. So we have just the light rays relabeled. It are precisely the same light rays as before. Yeah? If I consider all possible values for this constant of motion, I get precisely the same set of curves as when I consider all possible values for this constant of motion here. Well, another way of saying this is if I can take the wait a minute, what did I yeah, another way of doing it is reducing it to a second order equation. Actually, our geodesic equation is a second order equation, right? So we need initial conditions for r and for the derivative of r. Why here we have reduced it to the first order equation, and the reason was why this was possible was that we had the constant of motion. This allowed us to express one of the initial conditions, the derivative of r at the initial point, in terms of this constant of motion. If I want to write it really as a second order equation, I can do it in a way that these constants of motion drop out. Let me do it. Maybe this is more, yeah, then it's even better visible that it's precisely the same equation as without the constants of motion. I would divide by r4. dr by d phi squared is e squared c squared l squared plus lambda over 3 minus 1 over r squared plus rs over r. And now let's take the derivative with respect to phi. So the derivative with respect to phi is minus 4 r to the 5 dr by d phi dr, well, and another two terms, right? Then plus 1 over r4, 2 times dr d phi second derivative, 2r d phi squared. The constants drop out if I take the derivative, and then I get plus 2, no, on the other side I get plus 2 over r cubed dr by d phi minus rs over r squared dr by d phi. And now you see dr by d phi occurs in every term, so I can cancel it, and I get a second order differential equation, 2 over r to the 4 d2r d phi squared minus 4 over r to the 4 5 dr by d phi squared, and let me write this to the other side, minus 2 over r cubed plus rs over r is 0. That's the second order differential equation for our orbits, and you see there's no lambda in it. Lambda is gone, yeah, because we have differentiated it away here. So what does this mean? It means that, so that's a crucial observation. So when people observed this, and they did this many decades ago, so they said, okay, lambda has no influence on the light rays. Yeah? The light rays move in exactly the same way in the space-time with lambda as I do without lambda. And this is true if you look just at the coordinate picture of the light rays. Yeah, if you use these Schwarzschild coordinates, you use the r coordinate for plotting everything, and then you draw your light rays in this, in this coordinate system. Then the light ray looks precisely the same in space-time with lambda than without lambda. That's true. But does this really mean that the physics is the same? People for many, many years overlooked this, that this actually does not mean that the physics is the same. And the reason is that if we measure, for instance, angles, we have to do it with a metric. Yeah? The metric allows us to measure lengths and angles and things like that. So if we ask, for instance, under what angle is one light ray crossing another light ray? Yeah, we have two solutions to this equation, two light rays, they cross at a certain angle. Then we have to measure this angle to evaluate it with our metric. And in the metric, there is a lambda. So although the coordinate picture is the same with lambda and without lambda, the physics is not the same. Yeah, the measured angles are not the same. So the lambda does have an effect on the bending of light rays. And that's a very recent observation, actually. It was found around 2000 by a collaborator of my old teacher, Wolfgang Rindler. He did this together with Mustafa Ishak. So they are both in Dallas, in Texas, where I also spent a happy year, many, many years ago. And they published this paper, I think around 2000 or so, and it was really a great surprise. And there was a long debate about this. Some people said, no, that's not true. Actually, the lambda does not play any role for lensing. But I think now there is a consensus that it does play a role. So lambda has an influence on the light rays. And in order to illustrate this, I will repeat the calculation of the shadow of the black hole. We have done this for Schwarzschild. I will do it now again for the Kotler black hole, or for the black hole with lambda. And we will see that for an observer at the same coordinate r, the same radius coordinate r, actually the shadow will have a different radius from the Schwarzschild case. Well, you may ask, how do I know at which radius coordinate I am? That's again a fairly subtle question, but R does have a measurable meaning. I emphasized several times that there's a metric still on the board here. You see, from this term you read that the sphere R equals constant, T equal constants, has area 4 pi R squared. Yeah, so R is really something which is in principle measurable. Yeah, if you are to lay out a circle at radius r equal r naught and measure the circumference of this circle, you get what is this? 2 pi r, right? 2 pi r. Yeah, really with this r, it really gives you the measured length. That's something which can in principle be done. So in principle you can find out, and this is also true in the Kotler spacetime. Has nothing to do with lambda. Yeah, it's always true if the angular part has this form. So you can find out at which radius coordinate you are in the spacetime by way of measurement. If you have done this, now you observe the shadow, we do the calculation in a minute, and you see that the angular diameter depends on lambda. So that is something which is measurable in principle. So lambda does have an influence on the lensing properties of our black hole. So let's do this calculation. So oh no, I'm jumping ahead, sorry. So I'm not that, I have to do something before I do this. Remember, for the shadow it was crucial that there was a circular light ray at r equals 3/2 rs. And of course we have to calculate what's the analog of this now in this space-time. You already know that for lambda bigger than lambda critical there cannot be a circular light orbit. But in the other cases we might expect that there is one, and we will calculate where it is. So circular light orbit. Yeah, let me just write it this way. I think you know what I mean. A light like geodesic. So we look at this expression here. It's very good that we have derived this equation here where the second derivative is involved. Then it's very, very easy to do it. Because if I have a circular light orbit, then the r by d phi must be 0. And the second derivative must also be 0. So we must have the r by d phi equals 0 and second derivative equals 0. And then we find from this equation, which I've just marked star, we find that, oh, there's a mistake. I just have to check where I made a mistake. So what I have on the board gives me 2r cubed is rs over r. Oh, there are many mistakes. Actually, already, the dimension is already wrong. You see this? This is dimensionless. This has dimension 1 over length cubed. So where did I make a mistake? Well, there's a writing mistake here, but this is still wrong. Let me see. We should. I divided here by r to the 4. R squared is correct. But here, r divided by r to the 4 is 1 over r cubed, right? So there's a mistake. So here is, now I have to take the derivative. The derivative is now minus 3 divided, there's a 3, very good. 3 rs over r squared. And here I have plus 3. Oh yes, it was correct. So yes, now it's correct. Now it's correct. So 2 divided by r cubed is 3 rs r squared. This means r is what? R is 3 half rs. Surprise. Yeah.
Shouldn't it be r to the power of 4 in the denominator there? Because you have the derivative from 1 divided by r to the power of 3.
So you are talking about this term?
No, at the end term where you corrected the r to the power of 2 to the r to the power of 3.
Here?
Yes.
R divided by r to the 4 is r to the 3.
Yes, but then the derivative on the next
Yeah.
The dimensions will also not be
Minus, oh yeah, oh, it goes in the other direction. Goes in the other direction, yes, thank you. I hope it comes, yes, now the dimensions are correct, very good. And yes, so I multiply with r cubed, then I have 3 half rs is r. Yes, now it's correct, yes. So, surprise, right? That's exactly the same thing which we had in Schwarzschild. Well, of course, as soon as you realize that the differential equation is the same as it is in Schwarzschild, the solution must also be the same. Yeah? So, whatever the lambda is, the circular light orbit is always at 3 half rs. Please mind that rs is in general not the horizon. Yeah? Rs is the horizon only in the case lambda equals 0. For other lambda values, the horizon is in another place. But the light orbit, the photon orbit, is always at 3 half rs. By the way, 3 half rs was also the critical value for where the two horizons came together. Yeah? If lambda takes its critical value, this 4 over 9 rs squared, then the radius value at which this happens is also this here. Yeah? So the static region, in the case that you have two horizons, when it shrinks to 0, if you send lambda to lambda c, it shrinks around this value at 3 half rs. Okay, so we have, from this equation, we have deduced that a circular orbit must, the radius of a circular light orbit must satisfy this equation. We have not proved that there actually is a circular light orbit as this radius. What could go awry? Well, we have this constants of motion here, which is a square. And a square should certainly be non-negative. Yeah? So in order to know if this circular light orbit really exists, we have to check if it corresponds to a positive value for E squared over C squared L squared. Yeah? So then let's call this here double star. Then we have a 0 on the left-hand side. We are talking about a circular light orbit. We have E squared over C squared L squared plus lambda over 3 minus 1 over r squared. 1 over r squared is 1 over 9/4 rs squared plus rs over r cubed. That is 27 divided by 8 RS cubed. Okay, if I leave the E squared divided by C squared L squared on one side and put everything else to the other side, then I have, if I begin with this term, 4 over 9 RS squared minus 8 over 27 RS squared minus lambda over 3. Can I modify this a little bit? Yes, I think I multiply numerator and denominator with 3. Then I get 12 minus 8, that's 4, over 27 R squared minus lambda cubed. And this must be bigger or equal than 0, because it's a square. And now we see for which radius values, for which lambda values this is actually possible. And you see this is precisely the condition that lambda must be smaller than lambda critical. Yeah? So this means that lambda must be smaller than lambda critical. Yeah, I multiply with 3, then I have here 4 over 9 RS squared, and this was precisely lambda critical. Yeah? So it only works for the case where I have a static region. Yeah? So, well, actually, yeah, the limiting case is also included. Then the circular orbit is precisely at the degenerate horizon. Yeah? All these things coincide in the case lambda equal lambda critical. But the important thing is that if lambda is bigger than lambda critical, this light orbit does not exist. Yeah? Which was clear from the observation that that light must go towards the left in this diagram all the time. So now we can calculate the shadow. Now we know what we know at which radius value the circular light orbit occurs, and we also know the constants of motion, the value of the constants of motion. And that's enough for calculating the shadow. Oh, I forgot to mention that as in the Schwarzschild case, this light-like orbit is always unstable. You can easily read this from the expression star. You just have to check if a light ray starts tangential to a certain sphere, then this is 0. And then the question is if the second derivative is bigger or smaller than 0. Yeah, goes it away to in the increasing direction or in the decreasing direction. And you see, it depends on the sign of this term. So if R is bigger than Rs, then it goes outward. And if R is smaller than Rs, then it goes inward. So this means it's always unstable. No difference to the Schwarzschild case. And this means that light rays can spiral asymptotically towards this light-like orbit. And that gives rise to the shadow. So we have now the shadow of a Kotler black hole. So remember how we did this? So we have here it's supposed to be a sphere. This is 3/2 Rs. And then we have our black hole horizon at some smaller radius, not in general at Rs, at some other radius in general. And we have here our observer at a certain distance RO. It's supposed to be a static observer. So if there is a second horizon, so if we are in the case lambda between 0 and lambda critical, then of course the second horizon must be farther out than the position of our observer. Yeah? Because if the observer is behind the horizon, then he couldn't receive any signals from the neighborhood of the black hole. So, and what did we do? We sent light rays into the past from this position, and we asked for the particular light ray which spirals asymptotically towards the light sphere. Doesn't look like a sphere at all. Not much better. Okay, and what we want to find out is this angle. I think I called it theta in the Schwarzschild case. So this is a angular radius of the shadow. And well, we do it with the same construction. Let's call this again delta y, this delta x, and then we have the tangent of theta is delta y divided by delta x, well, strictly speaking, in the limit that delta x goes to 0, so that I have here differentials rather than differences. And now let's see, this goes in the phi direction. Do we have the metric still on the board? No, but I hope you remember what the angular part of the metric was. This is r d phi. This is r d phi, yes. And this here is in the radial direction. So the radial direction is dr divided by root 1 minus rs over r minus lambda over 3 r squared. Yeah, you see that is the delta y in the limit that it becomes infinitesimally small, and dr divided by this is a delta x. As can be read from the form of the metric, right? This is the thing which is in the denominator of the dr squared term. Okay, and d phi by dr, actually, we have calculated. I hope I did not erase this. Oops. dr by d phi is this here. So, well, let's square the whole thing. That's more convenient. So let me write the square of the tangent. Then I have r squared 1 minus rs over r minus lambda third r squared, and then divided by dr d phi squared. So divided by this expression here. So I have an r to the 4 in the numerator, in the denominator. Everything is in the denominator. Oops. So I have r4 e squared over c squared l squared minus lambda third. No, plus lambda third, sorry. Minus 1 over r squared plus rs over r cubed. And e squared over c squared l squared for this light ray, which asymptotically approaches our circular light orbit, must be the same as e squared divided by c squared l squared for this limiting orbit. Yeah, because if in the limits they become tangent, if the two geodesics become tangent to each other, then they must have the same constants of motion. So I have, tangent squared. Theta is, 1 minus rs over r minus lambda over 3 r squared divided by, no, I cannot do it in this way. R to the 4, and now I have to insert for e squared divided by c squared l squared plus lambda third. So I take this to the other side, and I have just this expression here. So this was, is it this here simply? Yeah, I think it is. So it is 4 divided by 27. Was this a square? Yes. So this here is this combination of the two constants. Minus 1 over, I should write RO instead of R everywhere. Yeah, I denoted this here, RO. So I have everything at R equal RO. So let me write RO. O squared plus RS. RO cubed. Okay, I think I can pull an R squared inside, maybe that's nicer. So that's this bracket here, then I have 1 minus RS over R minus lambda third RO squared Here I leave an RO squared outside and write here minus 1 plus RS over RO. Okay. And I think the formula becomes nicer if I write sine squared of theta. Sine squared of theta is, of course, sine squared of theta divided by 1. And 1 can be written as cosine squared theta plus sine squared theta. Okay, that's the same thing. And if I divide by sine squared, I get 1 over tangent squared plus 1 here. So I get 1 over, and now this expression here. Yes, the reciprocal of this, 4RO squared minus 1 plus RS RO, 27 RS squared, 1 minus RS R minus lambda third RO squared plus 1. So if I multiply numerator and denominator with this expression, I get what? So here I have minus 4 RO squared plus 4 RO RS, and now this multiplied with plus 1 plus 27 RS squared minus 27 RS cubed over R. Oh, that's not good. Squared minus lambda third RO squared RS squared. Why do I get such a horrible expression?
Sorry, I have one question.
Yeah.
I'm wondering, I don't know if I'm right, but you said in there the R by the phi should be the R to the power 4 also multiplied to the last two expressions, to the 1 divided by R squared and R is divided by R to the power of 3.
Wait a minute, you're talking about this equality?
Yes.
Okay, what did I do? R squared, then I wrote this here squared, and then I have in the denominator the R by the phi squared, and that's what I have written here. I hope so.
And
I think that's correct.
That was like, I just have here the equation 1 divided by R to the power 4, the R to phi in bracket 2 squared, and then there's this term inside. So if I'm not completely wrong, or my notations are wrong, then you have also to multiply the last two terms by R to the power of 4.
Because it's on the left.
Oh, yes, you're right. Yes. Yeah, thank you. Was this correct up here? Here. Yeah. I multiplied this term, but I forgot these two. Yes, you're right. So then I have here minus R squared in the numerator, right?
Yes.
And here I have an R. Okay.
Actually, then the next step, I don't understand why there are those two brackets in the center.
So slowly. So I do. I think I cancelled an R squared here, but I forgot that I have done this when I wrote this here. And then I inserted, for this constants of motion, this expression. I hope this was correct.
Why is there a multiplication?
For
those two curved brackets.
Right. It's like that, right? And we have now corrected this here. We approached the correct thing. Oops. So what I found here is definitely wrong. I realize this, so it's good that that we change it. So let's see if I can correct this. What do I do now? Probably the best thing is to leave this. Oops. And insert it here for this expression. Oops. So let's see. So I get, if I multiply this, I get 4 RO squared 27 RS squared minus RO to the 4 plus RS RO cubed. That's an RO here. And divided by, oops, 1 minus RS over R minus lambda third, and that's an RO. RO squared plus 1. Oops. Let's see if that's better. So I multiply with this expression. So I get here 4 RO squared over 27 RS squared. Oh, the dimensions are wrong. What has happened now? Squared. The dimensions are wrong.
You probably put the R0 squared out in bracket, therefore you don't need to, well, in this bracket.
I think that's it, right? How was that? And the 4 here. And the 4. Yes, I've just inserted this expression here. Okay, let me see. Next try. Oh my goodness. Well, I can divide by 1 or not, right? I think that's possible. Okay, but not more. And now I have RO cubed 4 27 RS squared minus RO plus RS divided by this here. Oops. Plus 1. Okay. So let's see what we get here. Let's check the dimensions. Inverse length, length squared. Length by length, yes, that's fine. Length, 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 that's also fine. Yes, I think the dimensions at least are correct. That's a good start. 1 minus RS over RO minus lambda third RO squared. And here I have what? 4 by O cubed 27 RS squared minus RO, that's an O here, plus RS, and then minus 1 times this here. Minus RO. No, I had a plus 1 here. That was a plus. Plus RO minus RS. Ah, that's nice. Lambda third RO cubed. So you see minus RO plus RO plus RS minus RS. That's very good. So this is RO times 1 minus RS over RO minus lambda third RO squared, and that's the correct result. Lo and behold, minus lambda third RO cubed. I think we can divide by one more RO, right? Yeah, let me write it here. I think I can squeeze this here. I can divide by RO. I have 1 minus RS over RO minus lambda third RO squared divided by 4 divided by 27 RO squared RS squared minus lambda third RO squared. And that's supposed to be sine squared. So sine squared, of course, must first be non-negative, otherwise it doesn't work, right? So I should emphasize the first thing is the formula depends on lambda. Yeah, lambda stays inside this expression. So the diameter of the shadow, which is 2 theta, definitely depends on lambda. Yeah, if two observers are at the same R coordinate, one in a Schwarzschild spacetime, one in a Kotler spacetime with a different value of lambda, then they see a different size of the shadow. Of course, in both cases, the shadow is circular. We are in a spherically symmetric spacetime, so there the shadow is always circular, but the size, the diameter is different. And now the question is this for all possible values of lambda an allowed value? So this must be between 0 and 1, right? Sine squared of something must be between 0 and 1. Well, our observer is in the static region, so this expression is positive. And we see what's the condition on lambda, where the condition on lambda is precisely that lambda must be smaller than lambda critical. Yeah? So the first condition is that we must have sine squared of theta bigger or equal than 0 for observer in static region. That's what we want to consider. So we have that this here is positive. That 1 minus RS R naught minus the third R naught squared is bigger than 0. Yeah? That's the static region, the region where t is a time-like coordinate. That's where we put our observer. We must have, so this was a condition that the observer is in this region, we must have that this here is positive. So we must have 4 naught cubed divided by, no, I should look at this expression. R naught squared. 27 RS squared is, no, minus lambda over 3 squared must be bigger than 0. If I divide by R naught square, and if I multiply by 3, we have 4 over 9 RS squared bigger than lambda, lambda. I have to multiply it with 3. And this was precisely on our lambda critical. Yeah? So if lambda is bigger than lambda critical, then we don't have a static region, so this condition could not be satisfied, and then this also would give a contradiction. But if this is satisfied, if we have lambda smaller than lambda critical, maybe negative, yeah? Either negative or positive, but smaller than lambda c, then everything is fine, we see a shadow. At least this first condition is satisfied. We need the second condition. This is also supposed to be smaller or equal than 1. Let's check if this gives something additional, something new. So we know that this is positive, yeah, so we can multiply the whole thing with the denominator. So we have 1 minus RS RO minus lambda third RO squared is supposed to be smaller or equal than this here. It's positive, yeah? We have verified this, yeah? You remember, if you multiply inequalities with something, it only works if the thing is positive, yeah? If you multiply inequality with a negative quantity, you get something which is wrong. but this is positive. O squared divided by RS squared minus lambda third RO squared. That's what we must have. And clearly this goes away. And then we have 1 minus RS of RO. Let's take this to the other side. Then we see this is precisely lambda critical divided by 3 RO squared. Must be smaller or equal than 0. And this is but this is satisfied, because if lambda is smaller than lambda critical, then we have this condition satisfied. Yeah, in the limiting case, this is we have exactly the equality here. So if lambda is equal to lambda c, well, the whole thing is then a little bit degenerate, because then the two horizons come together. Our light orbit is at the same value, and also our observer must be at this point. Yeah, because he must be between the two horizons. If the two horizons come together, then he must also be there. And then, of course, the angle must be. So the observer is then here. The observer is here, right? And then, of course, the theta must be pi half, right? So it's just half of the sky is then dark. Okay, yeah, time is out already. Very bad. I was hoping that I could also say a little bit about time-like geodesics today. I will do that on Friday. We will then in particular discuss that in the Kotler spacetime we have not only an ISCO, you remember, the innermost stable circular orbit, we also have an OSCO, an outermost stable circular orbit. And we will briefly mention at least that there are not only homoclinic orbits, orbits which spiral towards an unstable circular orbit, but also heteroclinic orbits, which in one direction spiral against one unstable circular orbit, and if you follow this into the past, then they spiral against a different orbit. So they connect two unstable orbits. That's what one calls a heteroclinic orbit. This does not exist in Schwarzschild. In Kotler it exists. And maybe the most interesting thing is that we have an equality point. So with a positive cosmological constant, we have something which has a repellent effect. Those of you who have taken my GR course may remember that a positive cosmological constant gives in the Newtonian limit a repulsive force. So if you have a positive cosmological constant, then there is a point at a certain distance from our center where the gravitational attraction is balanced by the push of the cosmological constant. So you can put a particle there, then not breathe, leave it there. It's highly unstable, but if you just put it there, if you find the right position, then it will stay there. Just without orbiting, just at one point, it will just stick there. If you do it carefully enough. So that's maybe the most interesting new feature which occurs in the space-time with a cosmological constant. So it's mathematically quite nice, even if it's probably physically not very relevant. So I will spend, I guess, the 45 minutes on Friday on that. Okay, any questions about this? We have 3 or 4 minutes left, but I think it's no point in beginning with time-like geodesics. No question? Everything clear?
So, as far as I understand, the observers in this for this situation for lambda smaller than lambda critical can move only inward.
You mean lambda bigger than lambda critical?
No, I mean
lambda smaller than 0 is similar to Schwarzschild.
Okay, lambda bigger.
Lambda bigger than lambda critical. Then they can only move inward.
But can we approach to the outer horizon?
There is no horizon in this case. In this case, there is no horizon.
Okay, but
two horizons exist in the case that lambda is between 0 and lambda critical.
Well, okay, but this is what I want to ask. So can we approach to this outer horizon?
You can come arbitrarily close. Yes. Well, I have erased the light rays, but if you remember, the light cones they approach the horizon asymptotically. So you can never reach the horizon, but you can come arbitrarily close if you move at subluminal velocity. Any more questions?
I think we didn't calculate the two horizons explicitly, right?
The case, I calculated the value for lambda and the value where the two horizons come together last Friday.
I was just wondering, what would be the second horizon for our universe?
Very, very far outside. Very big, very big. Almost infinite. Yeah.
But that would be theoretically the border of the universe.
Yes,
and
yes.
we can expect that it might actually exist like that.
Yeah, well, I have to repeat that this model which we are using here is not a realistic model for any part of our universe.
We assume that the cosmological constant is positive, then it also means that we are assuming that the universe as a whole is kind of like one mass. I mean, if we go very far away and we expect that the universe is expanding, we can assume that it is like 1 point.
No. No, it's a good approximation to assume that the mass density is homogeneously distributed. That's what one does in the so-called Friedmann models. Yeah. So it's not a point here and then a big vacuum around it. It's rather everything homogeneously distributed over the whole universe. That's the usual assumption with which you start if you do cosmology. So it's completely different from what we consider here. Yeah, I would think that the second horizon actually has not much to do with our real world, but yeah, maybe just to get a feeling for what the mathematics can.
In the very first moments of the universe, it might have been an effect because then the mass was concentrated, or it was still.
No, it was still homogeneously distributed over the whole universe. The whole universe was smaller at that time, but there was no vacuum around it. Yeah. So these models say, well, in pre-relativistic times, people have thought about this. These so-called island universes, yeah, where you have a mass distribution with a finite diameter and then vacuum around it. So this have been world models which have been considered by some people, but that's not what we believe nowadays. So nowadays we believe that it's a good first assumption to assume that the mass density is homogeneous. So that's what we call the Hubble flow, right? That the universe is flowing with a certain fall velocity, and the density is everywhere approximately the same. Of course, it's an approximation. Yeah. So you take all the galaxies and distribute them quite evenly over the space. That's the simplest cosmological models with which we work today. And then, if you want to talk about inhomogeneities, then you introduce them as small perturbations. Yeah? Then you do perturbation theory. But that's a zeroth approximation for our universe, so to speak. Not these isolated masses. Okay, shall we call it a day? So, see you on Friday.